now I will start the fourth lecture of week 8 of this course, and in this lecture I will talk a little bit more about the reciprocal lattice that I just briefly introduced in the last lecture, and then I will get into the instrumental details of the X-ray diffractometer. So, we have already learnt about the Bragg scattering law, which tells you the condition for constructive interference of X-ray scattering of some sample. Now we want to put this into place in an instrument, put this to use in the form of an instrument, okay, and that is what we will do when we see the X-ray diffractometer. Okay. So, week 8 lecture 4 we are going to talk about reciprocal lattice and XRD instrumentation. XRD stands for X-ray diffractometer or X-ray diffraction. Okay. So, now we have talked about reciprocal lattice vectors in the context of cubic or orthorhombic structures, but we can write a general expression for reciprocal lattice vectors. So, suppose the Bravais lattice vectors, okay, and the basis, okay. So, the basis for this Bravais lattice vectors are A1, A2, A3. Okay. Then that means any Bravais lattice vector R is a linear combination N1 A1 So, that is any Bravais lattice translation vectors. So, this is where we start off with. We start off with A1, A2 and A3 as the primitive translation vectors for the Bravais lattice. Now, for the reciprocal lattice vectors, okay, we will denote them by B1. So, the notation is B1, B2, B3, and basically this arbitrary reciprocal lattice vector K can be written as a linear combination of B1, B2 and B3. Okay, so these are like this B1, B2 and B3 are like A1 and A2, A3 for the real lattice, for the Bravais lattice, and these are for the reciprocal lattice. Okay. Now the question is, what is the relation between how can B1, B2 and B3 be expressed in terms of A1, A2, A3? So you can write a general expression for an arbitrary lattice, okay, and that is the following. So, B1 is a vector that is perpendicular to it is actually perpendicular to the plane of A2 and A3, okay, and this is written in the following way. So, 2 pi, okay, and in the case of the case of the cubic lattice, you just had B1 was proportional to A1, okay, but in a more general case it is actually proportional to A2 cross A3, okay, and A2 cross A3 is a vector that is perpendicular to both A2 and A3, okay. So, this is a vector that is perpendicular to both A2 and A3, okay. So, let me, and there is the denominator is the volume of the cell, A1 dot A2 cross A3. Similarly, I can write B2 as 2 pi A3 3 cross A1. Okay, you have to follow a cyclic order divided by A1 dot A2 cross A3. And finally, you can write B3 as 2 pi A2 cross A3 So, that is B1, B2 and B3. Okay. So, this is the general expression and you can use this for any Bravais lattice. Okay. So, this can be used for any Bravais lattice. Now, a few things about the reciprocal lattice. Okay. So, the first thing is that reciprocal lattice is also a Bravais lattice. Okay. And I cannot emphasize this enough. Okay. Okay, I cannot emphasize this enough. Okay, it is a Bravais. It should be one of the 14 Bravais lattices. Okay, so it should be Bravais lattice. The second point is that the Bravais lattice can be primitive, body centered, face centered, C centered, etc. Okay. So, the reciprocal lattice can also be, so that means reciprocal lattice can also be any of these. So, what is important is that the lattice translation vectors A1, A2 and A3 should be properly chosen. For the lattice. Okay, this is another important point which so for example, if you have a face centered cubic lattice, then A1, A2 and A3 will be different from a body centered cubic lattice or a simple cubic lattice. Okay. So, these are things to be kept in mind when you are dealing with reciprocal lattice vectors. Okay, I won't. I mean, we will keep looking at. We'll keep seeing reciprocal lattice vectors as we go along. Okay, but as we go along, both in X-ray diffraction and in band theory of solids. Okay, so but I'll stop discussing the concept of reciprocal lattice vectors for now, and now I want to go to the instrumental setup for the X-ray diffractometer. So, a typical X-ray diffractometer consists of a source of X-rays. Okay, so I'll just show it this way: source. Okay, and from this source there are these X-ray beams that are coming. Typically, they are a series of parallel X-ray beams. Okay, and they typically fall on some sample. And when they fall off the sample, they are scattered in all directions. Okay. And basically there is a detector this is a detector D, detector, and typically this detector can be rotated, so that you can pick up the scattering at different angles. Okay. So this is the general setup of the X-ray diffractometer. So we see that there are three main components. There is the source of X-rays. So these are X-rays, source of X-rays. Okay. Then there is the sample that you are using, and in the sample there are different ways to prepare the sample. Okay. So the sample preparation will be one of the topics that we look at, and the last part is the detector. Okay. So this is the general setup of the X-ray diffractometer, of any X-ray diffractometer. In fact this is typical for almost all spectroscopic instruments. Okay. So now let us look in detail about at each of these. Let us look at the X-ray sources. Okay. So if you how can you generate X-rays? Okay. Now typically the way to, I mean, X-rays have a wavelength that is typically of the order of 10 raised to minus 8 meters to 10 raised to minus 11 meters. Okay. So this typically this works out to about 100 angstroms to 0.1 angstroms. Okay. So they are very short wavelength and very high energy beams. Okay. So how do you generate X-rays? Okay. So the typical way you will generate X-rays is actually to to generate X-rays you have created by bombarding source material with accelerated electrons. So what I mean is the following, that you have a source material, okay, and you hit it with electrons, okay, and if you bombard it with very high energy electrons, okay, then these electrons will collide with the atoms of the source, okay, and and one of the things they do when they collide with the atoms of the source is that this electron, okay, so will collide with this atom to ionize the atom, okay, and emit another electron, okay, emit a second electron. Okay. So now if these electrons are very high energy, okay, then this electron that is taken out from this atom A is a core electron. So in other words, this A plus is missing a core electron. That means a core electron means not from the valence shell, but one of the inner shells. So the electron in this atom A is the electron that is removed is a core electron. Removed, okay, and when this core electron is removed, okay, then one of the higher shell electrons, okay, will will go and fill that vacancy, and in the process it will generate X-ray radiation. So that means this A plus with core vacancy, okay, will go to A plus with outer shell vacancy, where so the electron from the outer shell will go to the core shell, and during this process this will generate X-rays. Okay. In other words, if you look at the energy levels of A, so if you take A, okay, you have the very low lying core shells. So this is the K shell, maybe the L shell, and so on, and then you will have the valence electrons way up here, okay, and or valence electrons will be somewhere here. Okay. Now what is happening is that an electron is being when this electron bombards A, then the ionization is taking place due to an electron going out of here. Electron is ionized from this A shell, and what will happen is one of these higher level shells will come down here. Okay, one of the electrons from the L or M shell will come, and when they land, they will give X-rays. So this is how X-rays are generated. Okay, and so the electron beam hits the sample and X-rays are generated. Okay. So we can do some fairly simple calculations to find out the wavelength of the X-rays. Okay. So if we see the electrons, the initial kinetic energy of the electrons. Okay. So the initial kinetic energy of the electrons is K E minus final K E So this difference between the initial kinetic energy of the electron and the final kinetic energy. So this electron, after it hits the sample, it goes with some final kinetic energy, okay. And so this difference between the initial and final kinetic energy should be equal to the energy of the X-ray beam, which is h c by lambda, where lambda is the wavelength of the X-ray. Okay. And so now clearly this if this final kinetic energy is 0, okay, that means all the initial kinetic energy of the electron is transferred into the X-ray beam, okay, then the wavelength will be the smallest, okay, or the energy of the X-ray will be the largest. So we can immediately write that the minimum value of wavelength, okay, that will correspond to h c divided by the initial kinetic energy, and the initial kinetic energy is we can write it as E times V, where E is the electronic charge and V is the voltage through which it is accelerated. Okay. So this kinetic energy, this initial kinetic energy, it depends on how much voltage it was accelerated by, okay, and we can show that it is equal to E times V. Okay. And now we see that h is Planck's constant, c is the speed of light, E is the charge of an electron. These three are fundamental numbers. So we can write this lambda min in terms of V, okay, we can, and this number, if you calculate, it comes to 12398 angstroms divided by V. So basically the wavelength, the minimum wavelength can be calculated of the X-ray, can be calculated using this expression. So if these electrons are accelerated through some potential V, okay, so V is the potential of acceleration of electrons, So, V is the potential of acceleration, and if they are accelerated through some potential V, then you can calculate this wavelength. Okay. So, this wavelength of the X-ray beam can be calculated, and typically this wavelength. So, the wavelength, the radiation that is obtained from an X-ray source okay. This has two parts. Okay. So, one part is a broad part and other is a monochromatic part. Okay. So, you have a broad part and a monochromatic part. Okay. The broad part is called is referred to as the Bremsstrahlung. You do not have to remember this name, but it is still useful to know. So, the broad part is called the Bremsstrahlung, and the monochromatic part is what we are interested in using for the X-rays, for the X-ray diffraction. So, the most common X-ray source is the copper K alpha radiation, okay, and in this you have a 2p to 1s transition. So, an electron from 2p transitions to 1s of copper, and the wavelength generated is 1.5418 angstroms. Okay, copper K alpha. This is one of the most common sources. Okay, this is actually it is a doublet. Actually, this appears as a doublet. Okay, two closely spaced peaks. Okay, so there is K alpha 1, which is 1.54051 angstroms, and K alpha 2, which is 1.54433 angstroms. Okay. Then there is a K beta of copper, okay, which involves a 3p to 1s, okay, and this has a wavelength of 1.3922. So, this is much higher energy. Okay. So, if you look at the emission spectrum of copper, okay, if you look at the emission spectrum of copper, okay, then you will see that you have a broad part, which is the Bremsstrahlung, okay, and then on top of that you have the few peaks. So, this is the K beta and the K alpha, which is a doublet, okay, and K alpha is much more intense than the K beta. Okay. Now, if you want only a K alpha radiation, okay, then you use a filter. Okay. So, you use a filter, okay, which will absorb lot of the radiation except for the K alpha radiation. Okay. And one useful filter is nickel. So, nickel has an absorption spectrum that looks, this is the absorption spectrum of nickel. So, this is nickel absorption. So, it will absorb all the lights except those in the K alpha region. Okay. So, if you pass this X-ray through this nickel filter, okay, then you will get only the K alpha radiation. Okay. Now, there are other metals that can be used. that can be used. For example, you can use chromium, iron, of course you have seen copper, then you can see molybdenum, silver. Okay. And so, the K alpha for each of these, so for chromium is about 2.28 angstroms, iron is 1.93, molybdenum is 0.71 and silver is 0.56. Okay. So, as you go to heavier elements, the wavelength will decrease, wavelength of K alpha will decrease, because there and the energy will increase. So, this is a source of the X-ray radiation, but this X-rays that you generate using typical laboratory source are low intensity. And so one of the things you need to do is to, if you want a really high intensity source, okay, then you can use what is called a synchrotron source. So, synchrotron source is a high intensity source. This is very high intensity. And highly parallel. Okay. And synchrotron sources are usually several kilometers wide, Okay. And usually these are national facilities, national level facilities. In the sense that they will not be available in each institute or each college, rather there will be one for the whole nation or typically for a whole region. So, for example, the European Synchrotron Research Facility, ESRF, this is European Synchrotron Research Facility. This is in Grenoble, France, and it is used by researchers all over Europe. Okay, it is used by researchers all over Europe and even from India. Even from India, people sometimes send samples to the Synchrotron Research Facility if they want a very accurate measurement. Okay. And usually synchrotron sources have several instruments, not just an X-ray diffractometer. So, the synchrotron radiation is used for several different instruments. Okay. But X-rays from synchrotron are extremely powerful in order to detect very minute quantities and very accurately. Okay. Now, the next point I will just mention briefly here is the sample preparation and detectors. So, the sample can be either a powder or single crystal. Okay. And the powder XRD is the most widely used. Okay. And this is the one that is very widely used. It's the most, in some sense it's the easiest instrument. Single crystal is more sophisticated, okay, but still even single crystal X-ray diffraction is fairly widely used. Okay. So, slightly more sophisticated. Okay. obviously the sample that you prepare, your sample which you want to, whose X-ray diffraction you want to do, okay, that sample, in the first case you have to make it into a fine powder. Okay. In the second case you need to have a single crystal grown of it. Okay. And the last thing is about the detector. The detectors can be either a film or a counter. So, film detectors are not, I mean these are the older technology. Nowadays they usually have counters. So, you have some sort of counter. Okay. So, it could be some something that either like a photomultiplier tube or some such feature that will count the that will have a counter that will tell you the intensity of the X-ray diffraction pattern. So, at the end of all this, the resulting powder XRD pattern okay, and this is nowadays this is regularly seen in this format, looks like this. So, there is as a function of 2 theta, theta is a scattering angle, you have intensity as a function of 2 theta, and you typically have various peaks, something like this. Okay. So, this is what an X-ray diffraction pattern typically looks like. Okay. So, with this I will conclude this lecture. This is the 4th lecture of week 8, and in the next lecture we will review what we learnt in this week and do some practice problems. Thank you.